Good morning, viewers. Today, in applied physics, we are going to learn about capacitance. What you will learn is what is capacitance, what are different types of capacitors, what is the principle behind a capacitor, parallel plate capacitor, how it is formed, combination of capacitors in which we will learn about series and parallel combinations. Then how does a dielectric affect a parallel plate capacitor, whether the capacitance increases or the capacitance decreases. Then what is dielectric breakdown, and if time persists, we will learn about the applications of the capacitors. First of all, you should know what is the difference between conductors, insulators and dielectrics. We can differentiate them by learning what are free electrons. The electrons, which are the outermost electrons in the atom, they are loosely bound to the nucleus. When the atoms are packed together, the loosely bound electrons, they are set free, means the atoms are not able to have any force on them, so they roam about within the body of the solid. These electrons, which can freely roam around, are called free electrons. Those substances which have a large number of free electrons, they are called conductors. Approximately, there are around 10 to the power 22 free electrons per cc in a conductor. The substances which have very small number of free electrons, they are called insulators. Then what is a dielectric? Dielectric is a word which comes from Greek, means dia plus electric. Dia means through. So dielectric materials are those materials in which a steady electric field can be set up without causing any appreciable flow of current. Let us see what happens when you place a conductor in an external electric field. So, let us consider a conductor ABCD, which is placed in an external electric field. The free electrons experience electric force opposite to the electric field, and they start drifting towards the side ABC of the conductor. When a conductor is placed in an external field, equal and opposite charges are induced on its two sides. These induced charges, they are called bound charges. Why do we call them bound charges? Because these charges, they are going to disappear as soon as the electric field that has been applied externally is withdrawn. Induced charges do not affect the electric potential of the conductor, and its outer surface continues as an equipotential surface. Remember that electric field is always normal to the surface of the conductor. Now, what do these induced charges do? What is the effect of these charges? Basically, the presence of these induced charges sets up an electric field within the dielectric, say EI, which is directed opposite to the external electric field. Magnitude of electric field due to induced charges is equal to that of electric field, and so net electric field within the conductor, it is 0. Then what is a capacitor? A device to store a large amount of charge. So, capacitor is a device for storing a large amount of charge, or you can also say that it is a device which consists of two or more conductors which are arranged so as to obtain a higher capacitance. Now, let us define capacitance. If you give some electric potential to a conductor, you will find that electric potential varies directly as the charge on the conductor. So, you can say that charge is directly proportional to the potential, or the ratio of charge to potential of a conductor is always constant, and this constant, which is the constant of proportionality, is called capacitance. So, you can say that capacitance of a conductor is the ratio of charge to the potential applied to the conductor. Then what is the unit of capacitance? Remember, unit of capacitance is farad. If charge on the conductor is 1 coulomb, potential given to it is 1 volt, then we say that capacitance of the conductor is 1 farad. So, 1 farad is the capacitance of a conductor if it acquires a potential of 1 volt when 1 coulomb of charge is placed on it. How to calculate the capacitance of a spherical conductor? If you have a spherical conductor of radius r, say, and let us say we place a charge q on the sphere, that is the spherical conductor, then you should know from the definition of potential that potential of the conductor is given by q upon 4 pi epsilon naught r. Just now we have defined capacitance as the ratio of charge to potential. Put the value of V there, you will find that capacitance comes out to be 4 pi epsilon naught r. So, in the case of a spherical conductor, we can say that capacitance is directly proportional to the radius of the spherical conductor. Now, let us see what is the principle behind a parallel plate capacitor. First, let us consider plate P1, this plate. Let this plate be given a charge q. When you place a charge on a conductor, we have just now studied that its potential increases. Let us say its potential is V. Then capacitance, which is the ratio of charge to potential, is given by q by V. Now, what we do? We bring another plate P2 near to P1. You might have studied electrostatic induction. So, when you bring this plate P2 nearer to P1, the positive charge on P1 induces negative charge on the inner side of the plate P2 and positive charge on the outer side of plate P2. So, if we had put q charge on P1, then minus q charge gets induced on P2 and plus q charge gets induced on the outer surface of plate P2. This negative charge, this has come because we have placed a positive charge on P1 and this positive charge has induced negative charge. So, this negative charge is called bound charge and this positive charge on the outer surface is called free charge. Now, we ground the outer surface of plate P2. So, free positive charge on P2 flows over to the earth and only negative charge is left on plate P2. Now, what you have? That you have a negative charge and a positive charge. So, the presence of this bound negative charge on P2 decreases the potential of P1. If the potential of P1 gets decreased, you can supply more charge to plate P1 so that its potential can be raised to its initial value. When you supply more charge to this plate P1, it will induce again a negative charge on the inner side of plate P2 and positive charge on the outer side of plate P2. Again, this larger charge that gets induced on this will decrease the potential. So, this way you can put any amount of charge on the capacitor, but this is the ideal condition. The amount of charge that can be stored on a capacitor is not limited by its capacitance. Theoretically, you can place any amount of charge on the capacitor, but as the charge increases, potential difference between the plates also increases until the dielectric between the plates can no longer withstand the potential gradient. Potential gradient is potential per unit distance, and the charge then leaks from one plate to the other through the medium which is inside the or in between the plates of the capacitor. What happens? Dielectric gets punctured, the capacitor breaks down. So, there is a limit to the maximum charge. The maximum charge that can be stored on a capacitor depends on the nature of the medium, that is the dielectric which has been inserted between the plates of the capacitor. Now, let us study about permittivity and relative permittivity. You can place different materials in between the two plates of a capacitor. So, with the change in the dielectric material, different amounts of charge will deposit on the plates. The ratio of flux density to electric field intensity in the dielectric is what is called permittivity. In simple terms, permittivity means permit, a measure of how easily the dielectric will permit the establishment of flux lines within the dielectric is what is called permittivity. Relative permittivity, we sometimes also call it dielectric constant. It is the ratio of permittivity of any dielectric to that of a vacuum, means permittivity, ratio of permittivity of the medium to the permittivity of the vacuum. You can have different types of capacitors. You see on your screens, these are ceramic capacitors, these are bead like capacitors. Ceramic capacitors means the dielectric medium is ceramic. By using ceramic, you have a low loss factor, you have a reasonable level of stability. Ceramic dielectrics, they do not give as high level of capacitance per unit volume as some other types give you. So, ceramic capacitors basically range in value from a few picofarads to around 0.1 microfarad. Then electrolytic capacitor, most popular type of capacitor that is generally used. These capacitors have capacitances which are greater than about 1 microfarad. These have the highest levels of capacitance for a given volume. How do we construct it? Basically, you take two thin films of aluminum foil. One layer is covered with an oxide layer as an insulator, and then electrolyte soaked paper sheet is placed between them, and the two plates are wound around on one another and then placed into a can. These capacitors, they are polarized, that is, they can only be placed one way round in the circuit. If they are connected incorrectly, they can be damaged. Sometimes it has also happened that these capacitors, they have exploded. So, care should also be taken not to exceed the rated working voltage. Working voltage is always given on the capacitor. So, one should take it granted that you should use these capacitors and operate them in a value which is well below the value mentioned on the capacitor. So, here if you see this capacitor, the values are mentioned like this capacitor, it is of 2200 microfarad, 25 volt, means one should not exceed the potential difference of 25 volt. So, these capacitors, that is electrolytic capacitors, they have a wide tolerance. Typically, the values of the component may be stated with a tolerance of -50% to 100%. They are widely used in audio applications as coupling capacitors, and sometimes they are also used in smoothing applications for power supplies. They do not operate very well at high frequencies and are typically not used for frequencies which exceed 50 kilohertz, that is within the region 50 to 100 kilohertz, and these are marked with signs. Cathode of the capacitor is marked with a minus sign on the case, and in all these electrolytic capacitors, as you had seen, the values they are clearly mentioned. Then are plastic film capacitors. Again, all these capacitors are after the name of what type of dielectric is in between the plates of the capacitor. So, there are number of different types of plastic film capacitors. What type of plastic is being used? It may be polycarbonate, it may be polyester, it may be polystyrene. These are some of the common ones. And each and every kind of plastic that you use, it has its own properties which allows them to be used in specific applications. The value of these capacitors can range from several picofarads to a few microfarads. They are normally non-polar. We will study about polar and non-polar molecules further. In general, they are good general purpose capacitors that may be used for a variety of purposes, though their frequency performance is not very good as that of ceramic types. Then there are polypropylene capacitors. These capacitors are used when high tolerance is necessary. Then we use polyester capacitor of polypropylene film is used for the dielectric. It is said that there is almost no change of capacitance in these devices if they are used with frequencies of 100 kilohertz or lesser than 100 kilohertz. Then there is one silver mica capacitor. These are manufactured by plating silver electrodes directly onto the mica film dielectric. To achieve the required capacitance, several layers are used in this case. The value of silver mica capacitors range from a few picofarads to 2 or 3000 picofarads. They can still be obtained and are used where stability of value is of utmost importance and wherever you need to have low loss. Then there is tantalum capacitor. Now, when we use ordinary aluminum electrolytic capacitors, they are large in size. Now, wherever size of capacitor is important, we go in for tantalum capacitors. These are much smaller than aluminum electrolytic, and instead of using a film of oxide on aluminum, they use a film of oxide on tantalum. They do not normally have high working voltages. So, normally the maximum voltage is around 35 volt. So, this is a photograph of a tantalum capacitor. Like electrolytic capacitors, they are also polarized and are very intolerant of being reverse biased. And as we had studied in electrolytic capacitors, they also do often explode if they are placed under high stress. But due to their small size, they are very attractive for many applications. Then a supercapacitor, electric double layer capacitor. Why do we call it as a supercapacitor? Because it has a wonderful, you can say, capacity. The capacitance is around 0.47 farad, very large capacitance. So, care must be taken when you use such a capacitor which is having such a large capacitance in power supply circuits wherever they are used, because when they are used carelessly, then what will happen? The rectifier in the circuit, that will get destroyed, because these capacitors, which are supercapacitors, they have a high power, and so huge rush of current through the capacitor empties it. Means when the capacitor is empty, the current will be very large, which can destroy the rectifier of the power supply. Then is a variable capacitor. These are used in communication equipment, radios, televisions, VCR. You can adjust them by tuning their controls. Trimmers are internal adjusted capacitors that a consumer cannot adjust. These are all kinds of capacitors that are shown on your screens. You have electrolytic capacitors. This is a newer form. This is the older version used in 1940s. This is a paper capacitor. This is also a paper capacitor. Here you have a mica capacitor. This is ceramic capacitor. These are tantalum capacitors, as we had studied about these. This in the center is a variable air mica capacitor. Then what is a parallel plate capacitor? Parallel plate capacitor consists of two metallic plates parallel to each other, which are separated by a small distance d. Second plate, as we had learned on principle of a capacitor, is earth, means attached to the earth, so that the positive charge on the outer surface flows over to the earth. Again, as we studied in the principle of a parallel plate capacitor, that when you supply a certain charge, say plus q on P1, it will induce a charge minus q, which is bound charge on the inner plate of B, and positive charge on the outer plate will move on to the earth. Let us say that the plate area is A, and say the distance between these two plates is d. Then you know the relation between electric field and potential and distance, that electric field is negative of the potential gradient. Potential gradient is potential change in potential per unit distance. This means we can write down potential as electric field into distance. And in Gauss' law, we had studied that electric field in between the plates, parallel plates, which are having same kinds of surface charge densities, but of opposite polarity, is given as sigma over epsilon naught. So, E is sigma upon epsilon naught into d, where sigma is what? It is the surface charge density. Capacitance is defined as a ratio of charge to the potential. So, put the value of V here, you get C as epsilon naught q upon sigma d. But what is sigma? Surface charge density, charge per unit area. This means charge is equal to surface charge density into area. Put the value here, you get C as epsilon naught A upon d. So, capacitance of a parallel plate capacitor is given as epsilon naught, which is permittivity of free space, the value being 8.854 into 10 to the power minus 12 multiplied by area and divided by distance. This means capacitance depends upon area of the plates. You increase the area, capacitance increases, inversely proportional to the distance between the plates. Decrease the distance, the capacitance will increase, and also on the medium in between the plates. In combination of capacitors, first is series grouping of capacitors. Let us consider three capacitors. Say the value of these capacitors are C1, say this is C1, C2 and C3. second plate of C1 capacitor is joined to the first of the C2. Second of C2 is joined to the first plate of C3, and the second plate of C3, that is capacitor 3, is earth. This is how we say that they are combined in series. Now, let a charge plus Q be placed on plate A of capacitor C1. So, this means we place plus Q charge here. What will this plus Q charge do? It will induce minus Q charge on the inner plate of B and plus Q on the outer plate of B. The charge plus Q on the outer plate of B gets transferred to the first plate of C, which induces minus Q charge on inner side of D and plus Q on outer side of D. This charge gets transferred to plate E. This induces charge minus Q on inner plate of C3 and plus Q charge on outer plate of C3, that is F plate. This plus Q charge moves over to the earth. What happens here then? What do you see? We had given just a charge plus Q to A. This has minus Q charge, this has plus Q charge, minus Q charge, and so on. This means charge on each capacitor is same. So, what divides? Potential divides. Each capacitor has a different potential over it. As you see in the diagram, V1 potential is there on C1 capacitor, V2 potential is there on C2 capacitor, V3 potential is there on C3 capacitor. Again, this is shown in this diagram. V1 on the first capacitor, V2 on second capacitor, V3 on third capacitor. Charge is same. This means V is equal to V1 plus V2 plus V3. So, V is equal to Q upon C. V1 you will write as, because charge is same, Q upon C1. In the second capacitor, V2 you will write as Q upon C2. V3 you will write as Q upon C3. Q cancels, you get 1 over C equal to 1 over C1 plus 1 over C2 plus 1 over C3. Then is parallel grouping of capacitors. Here what you see, that first plate of each capacitor is connected to one point and the second plate of each capacitor is connected to the second point. So, the points are common. These three plates, that is the first plates, they have a common point here, and the second plates of the capacitors C1, C2 and C3 have a common point. But because capacitance is different, they will require different charge. But potential difference, which is the difference of potential between 2 points, as the 2 points are same, so potential on each capacitor is same, but charge is different. So, in parallel grouping of capacitors, potential on each capacitor is same, but here charge divides. Q is equal to Q1 plus Q2 plus Q3. What is C? C is Q upon V. So, Q is equal to C into V. Q is equal to C into V. Q1 is C1 into V. Q2 is C2 into V. So, here the capacitance is given by C1 plus C2 plus C3, whereas in series it is 1 over C equal to 1 over C1 plus 1 over C2 plus 1 over C3. So, it is different from that of the series combination. Now, let us talk about polar and non-polar molecules. When center of positive charge coincides with the center of negative charge, the molecule is said to be non-polar molecule, because such a molecule has no dipole moment. What is a dipole? Two equal and opposite charges separated by a certain vector distance between them. So, they will have a dipole moment. But as the center of negative charge and center of positive charges coincide, these molecules which are non-polar molecules, because they have no dipole moment. There are certain molecules such as ammonia, carbon dioxide and water, in which the centers of positive charge are separated from center of negative charge.